All right. So our next speaker is Professor uh, Jin.Chi, right? Professor Shi is. I know you work from reinforcement learning. You sort of prove this regret bound for this Q learning. I really enjoyed that reading that paper. So please tell us your latest project. And I saw this Goedel-Prover complaint. So please tell us about it.
Uh, yeah. Hi, everyone. It's very nice to meet you guys. Just one second. Can you guys see my screen on
Yes,
the slide?
yes,
Okay.
thank you.
Yeah. Hello, everyone. Yeah, it's very nice to meet you guys. And also thanks for the invitation. I'm really happy to talk here. Yes, I was originally worked mostly in learning theory and non-convex optimization and reinforcement learning theory. And recently, I really I'm very excited to share our very recent projects on this Goedel-Prover, which is doing the frontier model or achieving the state-of-art performance for open source automatic theory proving. It's essentially just the link prover for the formal math. I didn't know before this workshop that Don was talking right before me on this exactly same topic on the formal math. So I really like Don give a very good high level overviews on what is the overall goals and the challenges of the field. And today I'm going to talk a little bit more on concrete models, how we build the model and how we're going to achieve that kind of performance. And this is like a very recent effort. We just announced our model. Now it's on Hugging Face and also the homepage on website last week. And also today, Yong Lin and Shangge Tang, who are the leaders of this project, is also in the audience. And if you have technical questions, I think they should also able to help answering those. Okay, so let's start. We're talking about this formal math, and basically we're first we started to work on this formal math because we really see the amazing reasoning ability of the language model. For example, you probably already heard in the last fall, OpenAI O1 claim like they have a very big leap on the reasoning, and recently DeepSeek R1 also achieved like similar performance. So when those people talk about reasoning, usually it's really about math, about coding, and about also a lot of other PhD level problems like physics, chemistry, or something. So this is a picture they showed on how much achievement they get from O1. So for example, the previous generation of model GPT-4o is only like 10% on this competition math data set, which is AMY, while O1 is able to now achieve like 83%. So similarly also for competition code and also for some like graduate level question answering. And I personally really amazed by those performance. And when I tested it, I really I'm very excited to see like they actually able to provide some very good reasonings on how to solve the problems. So this is an example when we for example, ask those questions about some mathematical problems to one of the state-of-art models like Cloud 3.5. And this is the answer he get. Like he provide a bunch of reasoning steps, like first step, second step, six until seven step, and eventually tell you the answer, what is the final answer you get. So then the first question I have is like how we evaluate those those performance. For example, here we say that 83% accuracy or like 13% accuracy. What does this accuracy mean? So there are two things, essentially. One is just a single final answer. And the second thing is a lot of the intermediate reasoning steps. Like when we do the math problem, we also talk about we need to get the step correct. So all the accuracies in the last slides is actually computed purely based on the final answer. So we don't check intermediate steps at all. We just look at the final answer. If it's matched the golden answer provided in the benchmark data set, and then we just say it's correct. But this is like the previous approach, or this is called like informal math. But the real question is, like I work a lot on the theory, like machine learning theory. So I do care about you need to get the intermediate step correct to get the final answer. So how should we check the correctness of intermediate steps? And I would also argue there are a lot of scenarios. For example, the intermediate steps are really important. Maybe the final steps final answer you can guess. For example, in the IMO, they even tell you the final answer. They directly tell you what you want to prove. And so for those problems, you really want to know whether you can get the correct intermediate steps. So of course, if you just write this intermediate steps in the natural language in the informal math way, it's very difficult to check. Like you need to employ some human to check it, which is like very costing a lot of times, and also it prone to a lot of errors. So this is why people also introduced the formal math. Okay, formal math essentially, instead of like writing everything or reasoning in English, we write this reasoning steps in like some formal language. For example, there are Ling, there are also Isabella, there are a bunch of like different language developed by the formal math community. And the most important thing there is we have a compiler, or we have like some proof assistant like Ling or Isabella. So basically we can just write a proof and we can feed this proof to Ling and compiler. And Ling compiler will immediately tell you whether this is a correct proof or this is like incorrect proof, like which step seems like problematic. So the whole point of doing this formal math, I believe, and a very big advantage is whatever proof you wrote, it's machine checkable. So machine is able to immediately tell you whether it's correct. So this gives us a way to tell whether our intermediate reasoning steps is correct. Okay. And the Ling, so this is basically the, you can think the interface of Ling. Ling is called like a proof assistant, which in our talk, we will basically just focus on Ling, although there are like Isabella or some other proof assistant systems. So Ling is, you can think you can think it's very similar to Python. I wrote some code on the left side, which is like my proof for the mathematical problems. And Ling can do a compilation, essentially like a Python compiler. So it compile, give you something, and it tells you some feedbacks, whether it's correct or whether it's wrong, which step is wrong. And the Ling is further can be very interactive. For example, you can even just type in some steps as a like library search, which just tell the Ling interactive proof assistant to suggest some like proof tactics to complete your proofs. Okay, so although like you might not be, you might have not heard like this formal math before this talk, or maybe, but I would like to say this actually have a huge impacts on the math community. Okay, first you probably already heard the alpha proof, which achieved like silver medal performance in the last summer in IMO, in the most challenging mathematical contest or competition in the world. And I think they essentially have two systems. One is for the geometry, alpha geometry, which use DDAR, so they're like formal systems. And the other system is more like for algebra and the number theory, which essentially use Ling. So in addition to this competition, Ling is also very important for like even pushing forward the research community, like math research. It's not much automatic formalization by machine learning, but more or less like it's mathematicians. They want to verify the previous theory, they're accurate, or they want to establish some collaborative efforts and to make sure everyone only work on some small components of the proof, and then they jointly is able to prove some like big theorem, and where Ling is like very important in playing in those aspects. Okay. So talking a lot about the intro, so basically the objective here is we want to use this formal math as a tool, and we want to essentially train some advanced machine learning systems or LLMs, or you can call it provers, that is capable of given some like Ling problems, and we can automatically generate some like correct Ling proofs that will pass the compiler and just essentially give the correct proofs. So which this talk, we actually introduce our system that's called Goedel-Prover, which is named after Gödel, a very famous mathematician, on this like formal systems. And it's an open source model that achieves state-of-the-art performance in automatic theorem proving. Okay, and our model is also out there. It's released on Hugging Face. Okay, any questions so far? Okay, so if no questions, I guess I will first talk about a little bit about evaluation, because I kind of like made a bold claim that we achieved the state-of-the-art performance. So I want to like convince you that we indeed achieved that. And so this goes to a question, how we evaluate the model and how we say some model is good, some model is bad. So I think Don kind of like mentioned a very big challenge of formal math is the data scarcity. And I will also later talk about how we're gonna address part of that problems. So basically the takeaway there is the existing training data and evaluation is like somehow limited. So this basically is the major data sets and benchmarks in this open source community. So there are training data. Training data means essentially it's the data which comes with both problem statements in Lean and also the proofs in Lean. Okay, so we also give you the formal proofs for those problem statements. And there are evaluation data sets. A lot of those data sets only come with proofs, come with statements. That is, we only give you the problems and there's no proofs. So we need our model to generate proofs ourselves and ask Lean compiler to check whether it's correct or not. So one of the very famous one is the mini-F12. Essentially, a lot of the model evaluated on this mini-F12, and we will talk in the next slides. It contains mathematical problems of a lot of different levels. So there are some very difficult ones. There are also some very simple ones. Okay. And there are also like proof nets and problem bench. We will also talk a little bit later. And also specifically the Pullman bench we'll talk later. It's basically just consists of a problem of the Pullman competition in American, which is like considered challenging mathematical problems for high school. Okay. So things we will focus a lot on mini-F12 benchmarks, and we'll just say that it's a problem which consists of like 244 problems of the validation and 244 problems in the test, and they consist of a very challenging problem like IMO, AMI, ACM, and also some like math questions of algebra at different level 5 to level 1, and number theory from level 5 to level 1, and also a bunch of other problems. Okay. So after we're talking about the kind of like the evaluation data set, we kind of evaluate the performance. We want to also talk about what is the SOTA models before our model. So and I would say there are to enable like a very fair comparison. There are two types of different systems for generating this formal math. One is this style of whole proof generation. Essentially, you have a language model that generates the whole proof given the problem in one path. So one representative model is like DeepSeek Prover, like DeepSeek V1, DeepSeek V1.5. And one very important metric in evaluating is like how many proofs you wrote, like you sampled before you get in one correct proof or something like that. So basically, we will say something like pass at 32 times 6400 means like you essentially generate something like 200K proofs. And as long as one of the proof is correct, one of the proof pass this Lean compiler, and then we say this, we solve that problem, okay? So this pass at n is a very important metric in evaluating this whole proof generation. And the other type is the tree search method. So instead of like generating a whole proof, we kind of like generating step by step. And after we generate one step, we use some tree search algorithm, can be either breadth first search or best first search or something, and to search what might be the best next steps to generate. Some representative model like internal LLMs and alpha proofs, the system for both, I think for both geometry and for this algebra are kind of like use this tree search type of approach. Okay, so to begin with, we'll first only compare with the whole proof generation systems because we are our model Goedel-Prover is a whole proof generation, but we also have some other ways to compare with other open source like tree search method internal LLMs. We don't compare to alpha proof because it's closed sourced and it's achieve very good performance, but so far the model is not open, so we cannot really test it on a lot of the data set. Okay, so first, as promised, I will first look at the mini-F12 data sets. And we first evaluated a pass at 32, where the prior state of art is a DeepSeek Prover, where they have some variance after supervised fine-tuning or after the reinforcement learning. They achieve at the path at 32, which is a relatively small budget like a sample inference time, and they achieve like roughly 50% of accuracy. While our model, when we pass at 32, we actually achieve 57% accuracy, which is like 7% better than the previous state of art. And you can also ask when we scale up the inference computation, how our model performs. So this is like the picture. Essentially, when we scale up from path at 32 to path at 64 or path at 33K or something, we can see some consistent improvements, a relatively big gap around the 7% performance difference between our model and the prior state of our DeepSeek Prover.
Sorry, Professor, can I ask a question?
Yeah, please.
Have you guys seen the STP prover from Tenguma?
Tengyu.
Yeah, Tenguma.
Yeah.
Have you guys compared against that? Because I think at least the numbers they report are.
Yeah, that's a very good question. I think they released the paper. I don't know if they released the model so far, and they released the paper like one day after we announced the model. And I think we look at the performance. I think they're also very good, but they're slightly worse than our performance in terms of the accurate. Like when you go to, I think they reported the test at 128 and also 3K, and both the numbers are slightly worse than our number. And I think I will also like to say later when we talk about the methodology, they actually use a quite different methodology to solve the data scarcity, which is also a very important direction. I think I really likes it.
Okay, thank you.
Thank you. Okay, and the second thing is we also like evaluate our model on the Pullman bench. As we mentioned earlier, this is like essentially a bench consisted of all the Pullman mathematical competition, which is a very challenging questions. And we achieved the first place, which we solved the 7 problems. And we achieved, I think the second model although is also solving the 7 problem, but it's not open source. And we rank first because we actually use less inference time and compute. We're passed at 128. 112. 512. Sorry. Yeah. Some other achievement is like a lean workbook we previously mentioned is a very big training data, but unfortunately only a very small fraction of the training data, they provide a tons of like problem statements, but only a small fraction of problem statements has proof in it. And so previous model or all the existing works only find like 15K, around 15K proofs for the entire lean workbook statements, where our model is able to find something like around 30K, almost double the number of proofs ever found in this like lean workbook. And this is also our overall performance on the across a bunch of data sets, including lean mini F2F, proof nets, and the formal Numina is some like internal Numina, internal data set we use as a benchmark.
How big the model is? Presumably you fine-tuned existing language model, is it?
Yeah, this is like a 7B. We fine-tune a 7B model
Okay,
from
so
the DeepSeek base.
I see. So it's based on DeepSeek base, the same exactly
base,
same base as DeepSeek
same
prover.
base model of the DeepSeek prover. Yeah.
I see. Okay, cool. Thanks.
Yeah, we kind of we see relatively consistent improvements over a bunch of benchmarks. Okay, so after we talk about our methodology, after I talk about our performance, I really want to say a little bit about how we achieve this. It turns out the overall methodology is not that complicated. Which I really like is very simple and also clean, which I think is a very good as a starting point to push forward the automatic theorem proving. Okay, so as Don mentioned, the very key challenge of this formal math is about the data scarcity. So although DeepSeek, although the alpha proof kind of like say a lot of this company kind of like says they auto-formalize a lot of big data sets, but unfortunately in the open source community, the data set and data available is like very, very rare. And you can see we roughly have more than 10 million informal questions in like informal math. However, for number of questions or number of proofs we have for formal math, unfortunately, it's significantly less. For example, we only have roughly like 400K formal problem statements and only have 15K formal proofs, which is like very, very small. And it's very difficult to train any like a good prover based on this small number of data. So the very first thing we need to do is we need to get like way more formal statements so that we can get a better, like way more, we need to basically get more statements and more proofs. For statements, we essentially use the route of auto-formalization. So we first collect a lot of formal and informal statement pairs. Essentially, those are the problems which we do have both. Those are the mathematical problem. We both have like the formal statements and informal statements. We have 140K from Lean Workbook, which they provide both. And we also have a separate 170K generated from the cloud. Okay, And the second thing is we need to train a formalizer because 100K problems is not quite enough. So in order to do that, we train our own formalizer. Essentially, we start from this Chen 32B model, and we feed in this formal and informal statement pairs, and we get the final language model using SFT, and that is our formalizer. And once we have a formalizer, essentially we can look at a much bigger informal data sets, which in our process, we specifically use the Numina data sets, and which consists of like around 800K mathematical problems of high quality mathematical problems, and we formalize them into formalized statements. And some issues about this directly auto-formalizing statements. The first thing is it might have a lot of syntactic error. For example, we need to formalize this in the LINQ statements, but some of them just have the wrong grammar and they won't pass the LINQ compiler. So we will do the compilation correctness test. Essentially, we just deploy the LINQ compiler, and if it doesn't work, for example, LINQ compiler returns some errors, and we will ask the model to we will like fix that. And the second thing is, even if it passed the syntactic, passed the grammar, it just might translate to some completely different problems than the original problem. So for example, informal problems might be something like this, and a formal problem might like missing some conditions, or eventually the question is just different questions. So in this case, we cannot really deploy human, like at the university, we don't have human resource to humanly check all the statements. So we will use the phase 4 and completeness test, which essentially we ask for large language model as an independent judge, and to independently judge like whether this problem is this is like the right translation, and based on a bunch of criteria, we can prompt in the language model, and then we ask them to do majority vote. Okay, and after these pipelines, eventually we arrive with more than 1 million formal statements that will pass both tests, and we will use those statements as our training data set. Okay. So this is purely about the problem statements. Okay, there's no proof in it, it's just questions. So after we get into questions, now questions how we can get the more proofs. So we use this iterative training, this pipeline to getting more proofs. So essentially, we will start with some base model. When we have base models, like for example, the first iteration of Goedel-Prover, which is just a DeepSeek base 7B, and we feed in a lot of our formal statements, and then we do inference, and the prover is able to generate some of the proofs. Okay. And after generating some of the proofs, and we pass over LINQ compiler, LINQ will verify it, and we see some proofs are correct, and we will add those proofs into our data set for the next iteration of training. Okay, and starting from base model, we do a next iteration of training. So through this iteration of training, we can get in more and more proofs, and we will adding more and more formal proofs into our data sets, and we can train based on the more and more proofs. And this is a way, our way of getting more formal proofs. Okay. So this is roughly the table we will show, like we conduct iterative training. So instead of training on more proofs, we also iteratively adding more statements, so that when model have like more capacity, so when we adding more statements, and the model is better. And we don't add more statements at the very first time to like one thing is to save computation, one second thing is not to confuse the model. Okay. So we kind of like increase the number of statements we feed into the data. We feed into our prover to generate proofs, and we can see our model consistently like solving more problems and generating more proofs based on like both LINQ workbook and also the Numina data set. Okay, and we can also show, we can also see like across multiple data sets, our iterative training up to some statistical error is like quite effective. It's kind of like monotonically increasing the performance over multiple iterations. Okay, yeah, this is essentially the recipe we have for the entire model. As I said, this is like essentially our first step in pushing the limit of this automatic formal theorem proving. And where we have the Goedel-Prover, our first version of the model, we improve state-of-the-art performance on mini F2F. We also achieve the first rank on Pullman benchmark, and we solve essentially double the number of problems we solved on the LINQ workbook. Okay, any questions so far about our methodology?
So the prover itself is the size is 32B from the base model.
The formalizer is the 32B. The prover itself is 7B.
I see. I see.
The formalizer is yes, 32B.
Okay. So why didn't you didn't using reinforcement learning for the training?
Yeah, I think this is what I want to talk about the future. As I said, like this is our first iteration of efforts, like on this Goedel projects. We intend to make this like a long-term projects, and we essentially try things one by one. And I really like about this project is like we currently make it very simple and clean, and we already achieve a lot of performance. And I think our philosophy is we want to make every component like really good. And before we kind of, instead of like throwing a bunch of things and having a little bit, and we want to make every component very good and eventually like getting like really pushing forward this field.
Okay, cool.
Yeah. And so according to future, we'll also talk a little about reinforcement learning. So I think a bunch of directions I feel very excited. We're kind of like planning to currently working on it. And one is about the informal proofs. So we talk about auto-formalization, and in our pipeline so far, we mostly just auto-formalize the statements, problem statements. We didn't really effectively use the informal proofs. While there are a lot of like a proof written in natural language, which potentially is helpful in training like a training model how to write the proofs. So we actually ourselves like we train some like two different kinds. One is like we directly train on DeepSeek proofs, like the proof in DeepSeek style, like generated by DeepSeek base, and we typically train based on that, which is a machine generated one. And the other one, we also train some language model, which directly from this auto-formalized proof, that is like using cloud or using some other model that's like first translate the informal proofs into formal, and then we train iterative train based on that. And we can see a very big difference in terms of style. For example, in the formal, the one trained from like directly from DeepSeek style proofs, like this is like essentially the problem statements. We have some theorem and we ask him this, and by this is like a entire problem statements. And eventually the prover just using one step to solve the problem. Like they just call some like very advanced techniques, norm nom, and it's kind of like a compilation of a bunch of small steps into like a big tactics, and you just call this tactics in the link and it solve the problem. Well, if we have some prover trained from this formalized proofs, it usually have like more steps, like similar to how humans solve it, like divide and conquer. We have some lemmas, like we have some like sub problems, like we have, and then we kind of solve these sub problems. I think one very interesting thing is we kind of like observe this style of system is able to solve some problems where the other style of system is not able to solve. They're both able to solve some problem, but they're also small number. One is able to solve, the other one is not able to solve. And I think the very interesting question is we want to like put them together into joint train a system which is able to solve like generate both style and solve both kind of problems. And unfortunately, so far, it seems like the joint training is still not working very well. And this is something we're investigating a lot and very interesting to do. And the other thing is that we also find this like a more like longer style proof, auto-formalized style proof have a bit problem of doing OOD generalization. For example, they train on Numina data set, and then when you like generalize to mini F2F, there are slightly distribution shift, and the performance like tank a lot more for this like auto-formalized proof. Maybe it's because longer is more complicated than this like a short and succinct style proof. The other thing we haven't used so far is so-called execution feedbacks. So far, we're just generating the whole proof and then we train on the proof. But Lean is an interactive proof assistant, so it will actually provide you a lot of feedbacks in terms of whether not just compilation error, but it also tell you like which step might be wrong. And you can even like, as I said earlier, like you can like type in some command like library search or something. They're able to suggest you some like tactics which might be able to solve the problems. And the other direction I think is very exciting is how we're going to incorporate those execution feedback into our system to further boost the performance. And finally, I also want to leverage more like about reinforcement learning. I think it's a very good opportunity into put reinforcement learning into our systems. And the very first thing we can try is, in addition to just supervised fine tuning, we can also do some IO fine tuning like IOHF or PPO, DPO, those kind of algorithm. And we also talk about leveraging execution feedback. Execution feedback is some sort of reward which we can leverage and using reinforcement learning. And finally, and something we can definitely try is also combine this with tree search methods. Okay, so that's basically concludes my talk. And as I mentioned, most of them is already published, and we have project websites, and our model is available on Hugging Face. And if you want to try, you can also download our codes on the GitHub. And we're currently preparing a technical report. It should be on archive very, very soon. Okay. And finally, I also want to acknowledge our team members, and they're really amazing team members. Without them, this project won't be there. And first, I really want to acknowledge Yonglin and Shange Tang. Yong is postdocs at Princeton, and Shange is currently PhD students. Both of them are leading the projects. They are really putting a lot of efforts into this projects, and also Bohan Yu and Jiawing Wu, who are our research intern from Tsinghua University. And next is Hongzhou Lin and Kaiyu Yang, who are providing a lot of very helpful suggestions and feedbacks for Lin, and also from this like mass competition background, and they're from Amazon and Meta. And Jali from Numina providing a lot of helpful data sets. And also, finally, I want to thank my colleagues, amazing colleagues at Princeton, with Mengzhou Xia and Jin.Chi Jin and Sanjay Arora. And right now we have a very big institute at Princeton, Princeton Language Institute, which is we have a lot of computer resource and supporting a lot of exciting projects in large language models. Okay, this concludes my talk. Thank you.
Thanks a lot. Yeah, the performance really encouraging. Yes. Do we have any questions?
Yeah, may I ask a question?
Mm-hmm. Yes, please.
Thank you very much, Professor, for your work. It's amazing solver that you guys produce, and your team. You guys should be proud. It's a truly cool thing. Mm-hmm. Yeah, I have a question about the formalizer, if you don't mind. So I noticed that these Lean-based formalizers, they typically work on transforming the informal statements to the Lean statements. Lean, mm-hmm. Like basically theorems that later can be targeted. And so therefore the solution, the proof that is constructed also in Lean. Do you guys think about now translating this Lean proof into the informal proof so it will be more readable for people to read? Because if you're not experienced in Lean, it's quite difficult to navigate in that scripted language.
Yeah, I think this is a very good direction. This is a slightly perpendicular to our like projects, but I think it's a very good direction about the interoperability, about the formal proofs we generated, and how do we translate it to some human readable stuff, essentially make it more accessible. We haven't
your formalizer. Do you think that it will be difficult for your auto formalization step to basically work in the reverse direction?
I think we can definitely try to train, like just directly trying to train SFT like based on these pairs, which I don't know. We haven't tried it, but I think it's promising, and we can probably try that as a like first step towards like investigating whether this is like a feasible approach. Agree.
Thank you. Thanks.
Thank you.
Yes. Do we have any other question? Professor Jin, I have one question, and you and also Sloan didn't mention about presentation. I think also the presentation seems quite important to me, and like particularly for the mass
representation you're talking about.
A representation. So there's I mean the math itself is quite diverse science as well. There's a lot of different sort of questions, and therefore require different representation of it.
Mm-hmm.
So do you think the current Ling or all this, all this proof assistant would be adequate?
I think this is a very good question. I think also in the end of Don's talk, I think someone also raised a question about that. I think in our experience, we kind of feel right now Ling seems like pretty good at solving this algebra and number theory type of problems. We kind of like already feel it might be struggle a little bit for like the geometry problems. I think one thing is because like the data is also very limited about the geometry problem. The other thing is also, I personally, I'm not an expert in like this formal, like in terms of like this community, like building those proof assistants. But I kind of feel they're like people haven't used it very much. And in terms of combinatorial problems, it might be also like challenging. But I kind of feel the language might be okay to explain it. It's just the nature problem is very difficult, and also maybe the tactics is not enough. But again, I'm not an expert in like building this proof assistance, so
yeah, and that also leading to the question is that this natural language could still have some opportunities if we have like a large amount of data, and then this although it's a natural language, but it's not necessary to be rigor, but it does have this advantage in terms of the generalization. So do you think that
saying like sorry, you're saying like generating the natural language proofs. I personally feel like we're kind of like will go to an era very fast. Essentially, a lot of data is generated by machine instead of human. I think essentially we're overwhelmed by machine generated data. And we already see like in the informal things, a lot of things them are a hallucination. I think also a very big problem, as I said, like about this informal methods, like how we verify those reasoning steps. And if eventually like there are like 32 billion or like tons of data which is generated by machine, and some of them are right, I think even now, like when we write an informal proof, we kind of like we need to hire a lot of TA or like a professor to grade those informal like answering, and some of them it's like very slow and require a lot of expertise. I just feel this is not a very good approach to scaling up the entire automatic system. So I do feel like formal system in this case have a lot of unique advantage in like checking those steps.
Okay, yeah, all right, thanks. Okay, let's thank Professor Jin again for the very exciting talk. Shall we move to the next speaker? Hello, Professor Hajashrizi. I'm not sure whether I pronounce it correct. It's not sure whether she arrived or not. Shanding, do you know?
I thought there's a break after my talk.
Oh, sorry. Let me just look at the schedule. Maybe I should go to open up the schedule. Okay. Okay, so time now. All right, so we still have about a few minutes actually. So we will start with next talk. We will start at 6:25 p.m. in London and 10:25 a.m. in US. Right. Okay. Yeah. So maybe let's have a few minutes break, and we'll come back. I think we'll come back in about 10 minutes or so.